All right, so we are going to work on our next lecture on pressure. So this is lecture number 2 for our fluids unit. So we'll go through our learning targets. I can actually define what pressure is, and I know that there's a lot of ideas about the word pressure, but we'll definitely get very in depth with it. I can derive the relationship between depth and pressure, so how deep you go if you think about if you were to go swimming in the lake. As you go deeper and deeper, the pressure is going to increase. That's really important for things like any kind of maritime thing when people are making submarines and things of that sort. And we'll have a lot of problems that have to do with things going under the water. I can define atmospheric pressure, so you live on a planet in which there is an atmosphere. That atmosphere is pushing down on you at all times. We're going to talk about that. I could talk about gauge pressure, so we'll talk about how atmospheric pressure and any other pressure that's pushing down on you at a certain point can add together. I can derive formulas for the relationship between two fluids in a U-tube, so this is a much different U-tube than what you are used to and watching this video on currently. This is a U-shaped tube that we will talk a lot about that will come up in quite a few problems also that you do. And then I can use my knowledge of pressure to explain how a barometer works. And if you remember from earth science, or possibly chemistry, if you took chemistry, a barometer it measures air pressure. Okay. So, when we talk about pressure, pressure is a scalar quantity. That's very important because I know how much that we care about vectors and scalars, right? You can't all tell me yes because you're on the other end of the computer, but scalar quantity, okay? And then the equation for pressure, we talk about pressure as being the force per unit area as stated up here. So pressure is equal to F over A, okay? And when we also look at that, we can say, okay, well, the unit then for that, I know that force is measured in newtons and that area is measured in meters squared if I'm doing SI units. So that means that this would be a Newton per meter squared, which is more commonly called a Pascal, which we just represent as PA. That definition of pressure is going to be true in any situation, whether we're talking about fluids. It doesn't matter what we're talking about. That is always going to be the case. Um, you can see from that equation that pressure is going to depend on force and area, and it's going to be very, very important to remember that. So if you think about which one is going to hurt more, getting your toe stepped on with the heel of a sneaker or with the heel of a high heel shoe, again, assuming the same person is wearing the shoe. So with that in mind, the high heel shoe is definitely going to hurt more because it's a smaller area and you're applying the same amount of force because it's the same person that's actually wearing the shoe. So if we continue looking at this, so we're looking at these two different containers and they have the same amount of water that is added to both the vessels as shown in the picture, and both of them also have the same mass. The circular bottom of vessel B has twice the diameter as that of vessel A. So if we take a look at these two vessels that are placed on a tabletop, we would want to think about how the pressure that vessel B exerts on the table compares to the pressure that vessel A exerts on the table. So if we look at these two things, we can see that this is a different diameter, but they have the same mass, and the same amount of water is added to these two vessels. So I'm going to give you a minute to think about that, and then we'll talk about it. Okay. So we know that they both exert the same force on the table because the only force that's being exerted is the weight of whatever fluid, in this case water, is in the containers. So they both exert the same force on the table due to the gravitational pull of Earth on the containers and the water. However, the area over which that force is exerted on the table is going to be smaller for vessel A. And to flip back to vessel A, you see the smaller diameter. Therefore, the pressure on the table is going to be larger. So by doubling diameter, the area of the bottom of B is going to be 4 times greater. So remember that just because if diameter is doubled, that does not mean that area is doubled, because we know that the area of something is dependent on the diameter squared or radius squared. Okay, so if it's a circular aperture, for example, we know that the diameter, or the area rather, is going to be pi d squared over 4, okay, or just pi r squared, right? So therefore, the pressure exerted on table by A is going to be 4 times larger than that exerted by B, okay? So we know that a fluid is made of a large number of molecules that are bouncing around the walls of the container. We kind of talked about that in our last portion of this unit. The net force of those molecules is always going to be perpendicular to the wall that the fluid is actually in. So this picture here represents a microscopic view of pressure, and that's going to apply to whether it's water in a beaker or helium gas in a balloon. Okay, so this applies to any kind of fluid. Remember that fluid does not just mean liquid. Fluid means both gas and liquid. Okay. So let's talk now if we're actually submerging an object. So suppose that a macroscopic object, and in case we don't remember macroscopic means that it is visible with the naked eye. So suppose a macroscopic object is submerged into a fluid. The fluid is going to exert a perpendicular force on every surface of the object. So that force divided by the area of contact of the surface is going to be the pressure that's exerted by the fluid upon a given part of the object. So we're going to see that a bit more mathematically when we talk about the relationship between depth and pressure, as we're going to do shortly here. So in the presence of gravity, a fluid exerts a greater pressure if it's at a greater depth. A submerged object is going to be pressed upon more strongly as it sinks lower into the liquid, and that is because of the weight of the column of liquid that's above it at this point. So you have to take into consideration, if I were to draw that, there's some column of liquid here that is above the center of mass of this object, and I didn't draw that very well, but I also didn't say to scale or define where the center of mass of this object was, but hopefully that makes sense as just the column of liquid that is above that object. So if we talk a little bit more about the relationship between depth and pressure, if you imagine a circular surface of area A that is resting at a depth h below the surface of a fluid, we can figure out the pressure that's actually acting upon the disk due to the weight and the column of fluid above it. So we have some disk, this circular surface that's here that's pointed to. So we know that pressure, as we defined before, P is equal to F over A. And we know that this is gravitational force in this case, and we're told that the weight is mg over A. I'm going to do something funny here, which is not going to make sense until I actually do it, so bear with me. I'm going to say that the height of the column is h, and I'm going to say that's now a over h. And that could make sense because I could cross these h's out, but bear with me here while we're doing this derivation, because area times h is going to be equal to volume, okay? And we're going to keep going with this, and it's going to make sense once this comes out on the other end based on our lectures, our lecture on density and the last thing. So this is going to be m, that was a terrible m, sorry, mgh over v, and we know that mass over volume is equal to density. So this makes it really, really nice to relate pressure between depth if we just know the density of the fluid that the object is submerged in. So this is going to be a really, really, really important equation. Do you have to know the derivation? No. Are you going to have to be able to understand some of the steps and get answers to problems based on this derivation? Yes. Okay. So I would say that it really is important to have a very good understanding of this derivation. Rather than just simply memorizing it. I know how much we would like to just memorize things, but that is not really going to be helpful if you're not able to make this transition in particular, depending on the variables that you're going to have in a problem. So, the pressure at any given point in a fluid is going to depend only on the density of the fluid, the depth, and the strength of the gravitational field. So the shape of the container makes no difference at all. That's a really big misconception in that the pressure is greater at some point versus another between these three containers in particular because they are different shapes, and that is not true, okay? That's going to be true for the fact that it has no bearing, the shape of the container has no bearing on the pressure is going to be the case for all incompressible fluids. Remember that an incompressible fluid has a fixed density no matter what depth you're at. So if it has a fixed density, that means that if P is equal to rho GH, no matter the depth, if density is constant, then the pressure at that point H is going to be constant as well. So we now need to talk a bit about atmospheric pressure. So at sea level on Earth, and you lived at sea level, it's a pretty good approximation here in Walworth/Macedon, New York. So at sea level on Earth, the atmospheric pressure is about 10 to the 5 pascals. You don't really need to remember the 1.01. I don't actually remember what they give you in your reference table. I'm pretty sure they just give you 10 to the 5. I am very used to using 1.01, so if you see me using that, I just wanted to throw that out there as well. Hard to teach an old dog new tricks sometimes, as we know from me writing different numbers when I go back and forth between regions as well. So we're going to call this 10 to the 5 pascals 1 atmosphere. And we recall that 1 Pascal is going to be equal to 1 Newton per square meter, which is what we defined when we looked at the unit derivation of a Pascal. So roughly speaking, that would be like spreading the weight of an apple over the surface of a card table, let's say. So on human scales, 1 Pascal is an extremely small quantity, okay? The atmospheric pressure is going to tell you how much all of the air above you in some column is going to weigh. So the air above 1 square meter, if you were to lay it out flat at sea level, would weigh around 100,000 newtons. So that would mean that a card table at sea level lies below roughly 10 metric tons of air, just to give you an idea of the difference between 10 to the 5 pascals versus 1 Pascal on the scale of an apple being spread across this card table, as opposed to the air above you. Okay. Gauge pressure is the next thing that we're going to talk about. So pressure gauges are very important on scuba diving gear. I don't know if any of you have ever been scuba diving. If you told me whether you had or not, I apologize that now I'm not remembering. So scuba diving gear, bicycle pumps, which I'm sure we've all pumped a bicycle at some point, any kind of industrial equipment, things of that nature. If you have ever put air in your tires before, if you drive a car, that's also another thing that's going to have some kind of pressure gauge, because if you inflate the tire too much, that's dangerous. If your tire is underinflated, that is also dangerous, and we can talk about both of those dangers and what would happen. Hopefully by the end of this lecture, it'll make a bit of sense why that would be dangerous. So most of the gauges are going to measure pressure that's either above or below atmospheric pressure, and that is called gauge pressure. So in the case of the fluid that's below the atmosphere, so let's say it's in a lake or an ocean, the gauge pressure is going to be equal to Pg is equal to rho GH. So that's what that gauge pressure is, and that's very important to know as well. Okay. Absolute pressure is going to be the sum of atmospheric pressure as well as the gauge pressure. So what that looks like as an equation, I will write for you here. So P is equal to P naught plus Pg, where this is absolute pressure. This is atmospheric. And this is gauge pressure. Okay. So U-tubes, like I said, are going to be very important. So if you have a U-shaped tube, you're going to know that the pressure at points A and B has to be equal because they're on the same horizontal line. However, we have two different liquids that are going to have different densities, so that must mean that points A and B have to be at different depths below this surface if the pressure is going to be the same at that point. Okay, So since oil is less dense than water, you're going to need a greater volume of oil to balance out the water. So U-tubes are going to help compare the densities of different liquids. And like I said, we're going to talk a lot about these. We will do a lot more problems with them than you probably want to, but you're all used to doing that by now. So using the formula rho GH, so I will write that down here. Using the formula, rho GH for the columns of liquid above points A and B, we're going to derive the following relationship between the densities of oil and water. So we know that at that point, the oil pressure has to be equal to the water pressure. Okay. And if we go back and look at the diagram, we know that if we use this equation, the density of oil times G times H, where the oil is at, is therefore going to be equal to the density of water times G. And when we look at that diagram, you should see that this should be, oh my gosh, minus little h, okay? That formula is going to assume that the tube has fixed diameter. So that just means that the tube is neither going to widen nor narrow. We will talk about cases that this is going to happen, but for that we'll have to use a bit of a different equation. We also assume that the fluids are stationary, so there's no velocity within the tube of the water and the oil. They are simply stationary at rest, okay? So the barometer, so Torricelli is who invented the barometer. He did this in order to measure atmospheric pressure. So sometimes air pressure is either described in millimeters or in inches of mercury. So a glass tube that is filled with mercury, it sits upside down in a container, which is called a reservoir here. That container also contains mercury. So as the mercury level in the glass tube falls, vacuum is created, and that means that there is no pressure that is at the top of the tube. So with that in mind, we can say, all right, well then the barometer is going to work by balancing the pressure due to the mercury in the glass tube against the atmospheric pressure. So at this point here, you have 1 atmosphere due to the air and 1 atmosphere due to the column of mercury. So if the pressure due to the column of mercury is less than the atmospheric pressure, then the mercury level in the glass tube is actually going to rise. But if the pressure due to the column of mercury is more than the atmospheric pressure, the mercury tube is going to fall. And remember that at this red line, every point along this red line, the pressure is going to be equal because it's at the same height. With this in mind, this is how we're able to tell air pressure when you guys did your, if I know you guys are seniors now and most of you did earth science in 8th grade, I think all of you did. You remember the weather station symbols that had like, here, let me give you an example. It was like, if you had this and it had a number here, like let's say it was 090. Now that would tell you whether you had to add a 10 or a 9 in front of this. So if this number was less than 500, you added a 10 in front of it and put a decimal here. Okay, that number, that's determined by a barometer, such as this right here. Okay, so very important in weather instruments, very important as to why we get certain weather that we get here. So let's do some examples. So a perpendicular force is applied to a certain area and produces a new pressure P. If the same force is applied to half the area, the new pressure on the surface is going to be what? Okay, so this one shouldn't be too tough. So we know that pressure is equal to F over A, which means that force is equal to P times A. So that means that if I have a same force that's applied to half the area, I'm changing this new pressure is what I'm trying to figure out. Let's call it P prime. And it's going to be A over 2 because I'm told that I'm having the area. So if the forces are equal, as stated in the problem, so same force applied to half the area, that was an awful line, sorry, but same force applied to half the area, then that means I could set this and this equal to each other. So PA is equal to P prime A over 2. The areas will cancel. That means that P prime, so this new pressure, is equal to twice the original pressure. And if you don't have to do all that out to figure out the answer, that's great. But I wanted to show you how I got it rather than just saying that it's obvious that it's twice. Okay. So a 50 kilogram person stands on a square board with sides of 2 meters. What is the pressure in pascals that is exerted by the ground on the ground by the board? And we're assuming that the board is massless, or it's at least negligible mass. Okay. So it's a square board that has, this is 2 meters and this is 2 meters. So the area of this is actually going to be 4 meters squared, because the area of a square is just length times width, or side times side, whatever you learned it as. We also know mass, so we can therefore figure out pressure because we have mass. We know that we're on planet Earth unless otherwise stated, and we have an area. So we know that pressure is equal to force over area. So the force that's exerted on the ground by the board is going to be the force due to gravity. So this is just plugging in numbers at this point. So that should be about 500 divided by 4, which should be pretty close to this number. So 4 cubes lie on a tabletop as shown. Which two are going to exert the same pressure on the table? So we're looking for something. We're looking for 2 answers here. Sorry. Here. We're looking for 2 answers here. All right. So let's take a look at this. So we have a density of 6 and a side of 2 centimeters. Note that the density is already in cubic centimeters, so we don't have to do anything there, so that's kind of nice. Okay. So we're trying to figure out which of these are going to exert the same pressure on the table. So we know that pressure is equal to rho g h. Okay. So for A, we know that g is going to be the same for all of these, so we don't actually need to put g in our equation because it's just all multiplied by the same thing. You can if you really want to. I'm not going to. I'm just going to say, okay, for A, this is going to be 6 grams per centimeter cubed times 2 centimeters is going to be 12 pascals. B is 4 grams per centimeter cubed times 3 centimeters. So that's 12 pascals. So we know that B and A are equal to each other, so that's good to know, but let's look at the others just in case. So C here, and I'm going to write it up here just because I'm running out of room. So C is 1 gram per centimeter cubed times 5 centimeters. So that's 5 pascals. That is not equal. Now let's look at the last one. D is 3 grams per cubic centimeter times 6 centimeters, which is 18 pascals. So we are correct in saying that A and B are equal to each other. There are 5 containers that are of the same fluid in a physics lab. We want to know which has the greatest pressure at the bottom of the container. So that's very important, at the bottom of the container, because if we were asking at the top of the container, this would be a much more difficult problem. But we need to take a look at the fact that we remember that the size of the container does not actually, or I'm sorry, the shape of the container does not actually matter. So the one that is going to have the greatest pressure at the bottom is going to be the one that's at the greatest height. And we could see from this that that is D. Okay, so this one is at the greatest depth. If we were to put an object here, then that would mean the one for D would experience the greatest pressure. Okay. Calculate the pressure due to the water at the bottom of a swimming pool that is 2 meters deep. Okay. So we're looking for pressure. Water, this is going to be very important. I can't remember if I mentioned this in the density lecture. I feel like I probably did. The density of water, or sometimes I'll write it rho H2O, if we have something else that's a W, is equal to 1,000 kilograms per meter cubed. And some of you will remember that from chemistry, those of you that actually took chemistry, but just to throw it on there so that we know that. So P is equal to rho GH. So this is 1,000 kilograms per meter cubed times 9.8 meters per second squared. And the swimming pool has a depth of 2 meters. When you calculate all this out, this is going to be 19,600 pascals. A diver in the ocean measures the gauge pressure in the water to be 515 kilopascals. Remember that the prefix K means kilo, which is 10 to the 3. And we're asked to calculate the absolute pressure. So I know that absolute pressure is equal to atmospheric pressure plus gauge pressure. So the gauge pressure is what's measured by the diver. So this is going to be the pressure of the atmosphere, which is 10 to the 5 pascals. And this is going to be added to this 515 kilopascals. So that's 515 times 10 to the 3 pascals. And that is going to be 6.15 times 10 to the 5 pascals when you calculate that out. Example number 6. Calculate the absolute pressure at the bottom of a swimming pool whose depth is 2 meters. So the nice thing is that this swimming pool is from a previous problem, so I know the gauge pressure at the bottom. I calculated that out above. I said that it was 19,600 pascals in example 5. Okay. So pressure is going to be equal to the atmospheric pressure plus that gauge pressure that I calculated. So that's 10 to the 5 pascals plus 1,000 or 19,600 pascals. So that's 120,600 pascals. Okay, and that is it for this set of notes. So hopefully this made a lot of sense. It'll start to get a bit more complicated when the fluids actually start moving around, because as of right now, we have not talked about any kind of fluid that has had any velocity whatsoever. So we will talk about that in the coming lectures.